Alright, this is problem number 4 on your test. I'm going to work it two ways. This is the problem that gave most of you the most difficulty. I think it really shouldn't have. So the particle begins from rest at a point positive 15 meters from the origin at time t equals 0 and begins accelerating at a constant 5 meter per second squared in the negative direction. At time t equals 4 seconds, the particle has reached a certain speed, it stops accelerating, and continues traveling with that same speed until t equals 7 seconds. What is its position relative to the origin, that's key, at t equals 7 seconds? In other words, how far has it moved away from the origin after 7 seconds of motion? So, first way I'm going to do this is kinematically. This is using the formulas you all are most familiar with, and then I will do it graphically. We'll look at it both ways, we'll get the same answer both ways. So, method 1. Kinematics. To do kinematics, we must remember that there is a time that the particle is accelerating, and there is a time that the particle is moving at a constant velocity. We must find the change in position of the particle for both of those times. So let's look at that now. Alright, so if we look at the first 4 seconds during which the particle is accelerating, the equation that I get to use is your favorite, the long nasty one. We have x final equals x initial plus v initial t plus 1/2 a t squared. Let's remember a few things. Initial velocity is 0. Acceleration is negative 5 meters per second squared. Be careful, that's not explicitly stated in the problem, even though it says 5 meters per second squared in the negative direction. Many of you forgot that negative sign. And lastly, time is 4 seconds. Plug everything in. Oh, one more thing. X initial was positive 15 meters. So let's plug everything in. Okay, initial position was 15 plus initial velocity 0 times 4 plus half times negative 5 times 4 squared. So that is 16, negative 80, negative 40, and 15. So 15 minus 40, that is negative 25 meters. In other words, after 4 seconds, the particle has moved from 15 meters in the positive direction backwards 25 meters. So it now sits at negative 25. Now, to find how far it went during the time interval between 4 seconds and 7 seconds, I first need to know how fast is it going after 4 seconds, because after 4 seconds, velocity is constant. So I need to find velocity after 4 seconds. That's very simple. V final equals V initial plus acceleration times time. Initial velocity is 0. Okay, so I get AT, which is negative 5 times 4, or negative 20 meters per second. I then know that delta x equals v times t. So I have x final equals x initial plus vt, which is, my initial position was negative 25 plus negative 20 times 4, excuse me, negative 20 times 3 easy mistake to make. Okay, remember it's 3 because we're looking at the time frame between 4 and 7. That's only 3 seconds. When you do the math, you get negative 25 plus a negative 60, or negative 85 meters. Alright, the other way to work this. So let me get another page in here and we'll make it make sense. So this is method 2. Graphically. Graphically allows you to see pictorially what the object is doing. I like it better. So let's start with what we are given, most definitely, is acceleration. So we know a value for A. So acceleration was given to us at negative 5 meters per second, and we were told that it lasts for 4 seconds. 1, 2, 3, 4. 1, 2, 3, 4, 5. So this is our negative 5 meters per second squared here. That lasts for 4 seconds. And then we are told that the acceleration goes to 0 and continues for 1, 2, 3 seconds. So the main things we need to focus on are our 4 seconds and our 7 seconds. Now, to jump from there to velocity. Okay, remember, what do? We integrate, okay, which big picture, area under the curve. Alright, now let's look at velocity versus time. So v versus t here, we're looking again, 7 seconds, 1, 2, 3, 4, 5, 6, 7. Now if we take the area under our acceleration versus time graph, so area, 4 seconds times negative 5 meters per second squared, I get negative 20 meters per second. So that tells me at t equals 4 seconds, v is negative 20 meters per second. Okay? And I know the initial of 0. Therefore, I can draw my graph. So I have initial velocity 0. Right? I break my y-axis up into 5, so 5, 10, 15, 20. So this is negative 20 meters per second here. Okay, my other value at 4 seconds was negative 20. So my velocity from 0 to 4 seconds looks as so. Then, from 4 seconds to 7 seconds, my velocity is constant, so it looks like that. Again, now, finally, go to position. What do? I integrate. Take the area. Do not overcomplicate this. This is a simple process, but it's easily overcomplicated. Okay? So I could draw a position versus time graph for you, but to make life easier, we are just physically going to take the area of these two shapes geometrically. So to find position, delta x equals area 1 plus area 2. Right? So area 1 is a triangle, so that's half base, which is 4 seconds, times height, which is negative 20 meters per second, plus area 2, which is 3 seconds, times negative 20 meters per second. Do the math, you get negative 100 meters. Now, before you freak out and say, Mr. Parham, that's wrong because the answer is not the same, you must remember one small piece of information, and I'm going to write it up here if you will allow me. Delta x equals x final minus x initial. We are looking for x final. Therefore, x final equals delta x plus x initial. Okay, our initial position was positive 15 meters, so I have negative 100 meters plus 15 meters, leaving you with negative 85 meters equals delta x final, and we are done. Both answers are the same. Excellent, wonderful. Life still good. Physics still works. Hope it helps.